This is FM2 Further Mechanics 2 from 2023. Let's go into question 1 here. So we're going to have just a basic formula here, of course, which is just the distance to the center of mass, we'll work with the x coordinate first. So the distance to the center of mass from the origin is 2a, times the total mass, which is just 3m plus 4m plus km, equals, and then this is a bit like taking moments, right? Like the first mass we can imagine is 2a away and weighs 3m. So it's that, plus then this times this, plus then, of course, lastly, this times this. And of course, you can cancel the m's and sort this out a bit, and you end up with this here eventually. I wrote it like that. I'm not really sure that that was actually the best idea. But anyway, then you just do the same thing with the y coordinates. So, the total distance that the y coordinate, the center of mass is in the y coordinate is 4a, times that by the total mass. So it's just the same thing, equals, and then take moments of each thing individually. This times this, plus this times this, plus this times this. Cancel the m's again, sort it all out. And here you end up with the simultaneous equation, right? So I think I divided one of these by, okay, so I said k was 2 over this, and then shoved it into there, and then just did some cross multiplying and solving, and you get both of the things there. And that is the first question done. Particle mass 2 moving along a smooth horizontal surface. So of course, we get out F equals ma, except we're not really going to use this version of F equals ma. A, of course, is the derivative of velocity, so we'll actually use F equals m dv by dt, because we have F in terms of v, and yeah, we have m, of course, as 2. So we can kind of treat this as a separable differential equation, which is what it is. So we can divide both sides by 2 plus v, times both sides by dt, and then we can, of course, integrate both sides to form an equation in terms of t and v. This just integrates to 2 lots of log 2 plus v, I think, plus c, of course. And this integrates to t. And yeah, we don't really need the plus c, because we're going to think about the time taken for it to get from 5 meters per second to 10 meters per second. So let's put in 10 meters per second and say that happens at t1, or put in 5 and say t1, and then 10 at t2, and then say the time it takes to get from 10 to 5 is just the difference between these times. So it's t2 minus t1 is our big T that we're looking for. And of course, this minus this, the c's will cancel, and you'll just end up taking away the 2 logs. You can divide logs when you're taking away, and so it just ends up being 2 lots of log 12 over 7, I guess, like this. And you could have just done a definite integral when you integrated here, I should say. You could just do the definite, which of course cancels the c anyway, and everything ends up being the same. But in any case, we'll get that as our answer there. Now it's talking about the distance moved by the particle. Well, that's of course x, so we're going to think about how to get an x out of this. And we use this formula here, F equals mv dv by dx, just to explain where that comes from, although you're just going to have to memorize it if you want to. We used this in the last question, of course, because a is the derivative of velocity. But of course, we could use some chain rule to say dv by dt is the same as dv by dx times dx by dt, because these x's would just kind of cancel and you'd end up with this here. But of course, what is dx by dt? Well, it's just v. So we end up with this here. Super useful, go into the exam knowing it. Anyway, now we can just do what we did before. F is still 2 plus v, m is still 2. We can do a separable differential equation here and write it like this, and then integrate both sides. Now, integrating this here isn't that easy, but you can use some classic tricks. Maybe write 2v as 4 plus 2v minus 4, because that's totally what it is, right? Like, the 4's just cancel. And now you can break the fraction here. And also maybe factorize out 2 from these first 2 terms to end up with this. Now, of course, these 2 things will cancel, and you'll just have 2 minus this. And this thing is super easy to integrate, because it's just another log. So you end up with another log. This integrates to x, of course. I should have put a plus c, and I totally forgot. But it doesn't matter, because I'm just going to do the same thing as I did before, which is d, the distance is gone. Just like the time it took to get from here to here, the distance is gone. It's just when you put in 10, to this here, and then you take away what happens when you put in 5. So it's almost like I'm just doing a definite integral between 10 and 5, I guess. But anyway, just take them away. The c's would cancel if I had actually bothered to remember writing a c, and you'll end up with this as the distance, and that is that one done here. The second of, I think, 4 center of mass questions is in front of us. We need to firstly look in the formula book, and we can see this formula here for a arc, because this is just a framework, right? There's nothing, these aren't solids, it's just wires, I guess. So the center of mass for an arc, which is just AB from the center here at O, is this. Now, this angle here is pi over 2, which means we need 2a to be pi over 2, because its center has angle 2a. So of course A, or alpha, I guess I should say, is pi over 4. So that means the center of mass, you put pi over 4 in here, and you end up with, then do some cancelling and stuff, and you get this. So that's the distance to the center of mass from the center. But that's a diagonal distance like this, right? What it wants is it wants the distance d from OA. So it wants this distance across here, is what it actually wants. But we have this distance here. But we can just look at the 1, 1 root 2 triangle, the 1, 1 right angled root 2 triangle, super, super nice triangle. If I just times this triangle by 2r over pi, I'll end up with this triangle here, which means, of course, if I have a diagonal distance of 2 root 2r over pi, which is what I do have, that means each of its two shorter lengths is just going to be 2r over pi as required. So, okay, this distance is 2r over pi. Given the distance of the center of mass is d, from the entire framework, we're going to do something very similar to what we did in question 1, which is firstly, this arc here also has this same distance away from this length over here, just because it's the same arc there, I guess. And we're only thinking about horizontal distances because we're thinking about the distance from OA, so I don't need to think about any vertical distances yet. R has a center of mass, this wire here has a center of mass of half r away from OA, of course, and this one a distance of r away. So, okay, now we can just do the same thing we did before, which is d, which is the kind of overall center of mass distance away from OA, times by the total mass, equals, and then just take moments, 2r over pi times the mass of this, which is essentially just the circumference, or the length of it, which is 2 pi r all the way around divided by 4. If you're working in radians, of course, you can just use the radians formula. Either way, you'll just get pi r over 2. Just 2 pi r over 4, I guess. Technically, I should have times everything here by a density factor, but of course it would all just cancel, so it goes away anyway. This is just the same as this because it's just representing this arc. And then, of course, the half r times this wire's weight, which is just r, I guess we can say. And then, of course, r times r for this one. If you put all of that together, you get this, because the pi's cancelled, so it makes it quite nice. And then you just divide and divide by r, because r is not 0. And then you end up with this here. The framework is pivoted at A. So, okay, it's held in equilibrium at A, I guess. And, of course, if you hold it at A, the center of mass is like somewhere, I mean, I don't know whether it's all the way down here, but it's this far away from this. So if you just strung this up at A, it would tip over such that this line here was, of course, vertical. So what you're going to need to do is you need to apply a force to the right to hold it as we're looking at it now, which is exactly what's happening. We're holding it such that AO is still vertical. So we're going to need to apply a force, and it says the force is at C, to hold that vertical. Of course, its weight is pulling straight down. And now we can just take moments about A to find the force, because the force is acting 2r away from A, where we're holding it. So just 2r down and the perpendicular force of F coming across. And W, we could kind of just imagine W shifting up to here. It's acting down, so pulling it clockwise. It's pulling it clockwise a distance of this away from A. So this times this, pulling clockwise, is going to be equal to this times this, pulling anti-clockwise, just doing moments from A there. And we'll end up dividing by 2r and ending up with this here as our answer. Question 4 then. So, okay, well, first, of course, we've got mg coming straight down. Annoyingly big M, which is just more annoying for me to type, but who cares? You guys weren't interested in that. But anyway, mg sine theta is here because, of course, alternate angles, this is theta. So this is mg sine theta, this is mg cos theta. And now we've got a couple more things to do. Of course, we've got acceleration into the center. If we're given just the velocity, the acceleration to the center is just v squared over r, where r is the radius of the circle it's going around, which is a. And of course, that's the acceleration going into the center. So now, kind of into the center, we can just do F equals ma. We can say this minus this equals m times the acceleration. So the acceleration is acting in this way. So it's going to be this one minus this one is equal to m times the acceleration towards the center. This is just a formula that you need to know going into the exam. It's different if it's angular velocity, and we'll see that one in a couple of questions' time. Anyway, we've got this now. We've also got that this distance here up to where P is a cos theta, because of course theta is here, this whole thing is A, so this is up to there is a cos theta, just doing SOHCAHTOA, I guess, or just because cos is next to the angle. And we can do conservation of energy here, because initially we have um, it's stationary, right? So the only energy we have is mgh, and h we can say is a, and then if it's some point around this circle here, we can say that mgh is mga cos theta because it's only got this much height now, but it's also got the half mv squared, the kinetic energy that it's now got when it's somewhere around the circle. Now, of course, we can rearrange one of these for v and put it into the other one, and we'll end up making an expression for r. So I think I cancelled all the m's from here and moved this term over here and factorized, and then I guess just times everything by 2 and put it into here. And then, of course, you can rearrange this for r, and these a's cancel, which is kind of them. Rearrange and refactorize this up, and you'll end up with what they wanted you to get. Find in terms of a and g the speed when the particle leaves the surface. Now, when it leaves the surface, that means that r is 0. If there's no reaction force, that means that it's going to slip off the surface. So we're just looking for r to be 0. Of course, we have this equation for r now, so we just set that equal to 0. Of course, mg can't be 0, so that means this is. And now you could solve this for theta, but it's actually unnecessary because you're being asked for the speed of a particle at the instant that it leaves. If you remember going back a second, we have a formula for the speed. It's just twice this, right? V squared is twice this. So let's put that back up here and just put in cos theta is 2/3. And then, of course, we can square root, and we'll end up with v is that. Question 5, more center of mass, then this time with a lamina. So they're asking us all the different things they can about center of mass here. And we need this formula for distance. It's saying distance from OB, so we're looking for the y coordinate that the center of mass is, which is y bar. And this is the formula we need. It's not in the formula book. So this is what we're going to need to do between 0 and 3, of course, because it's between 0 and 3 on the x across there. So, okay, well, y is just this. Now, this is actually just 18, because, of course, the integral of y dx between 3 and 0 is just the area that we're looking at here. They've told you the area is 18, so that's just 18. You can save yourself some time by not doing that. Otherwise, bring the half out here and square this entire function, and then just start integrating. And you can, I mean, this is not particularly complicated. You just put all the numbers in, and you'll eventually end up with this here. But yeah, you do just need to go in knowing this formula. Otherwise, you're not going to get questions like these. The next one, a light string, is attached now. I've just turned this picture over like this. Distance 3.6 is still applying because we've got 2 strings at O and A vertically upwards towards some ceiling, both hanging vertically. This one doesn't look amazingly vertical, but whatever. And it's hanging exactly so that OA is exactly horizontal, I think it says somewhere. So that means that the center of mass is straight down like this. And what we can do is we can maybe take moments, if we call the weight of the entire thing W. And then, of course, we can call the tension up this string lambda W, because that's what it says. We can take moments maybe from O and say 9 times lambda W must equal 3.6 times W. Things pulling upwards, same as things pulling downwards. And, of course, this ends up being super simple, and we get lambda as 0.4. And this dotted line ends up being completely pointless. I don't really know why I drew it, but yeah, whatever. Question number 6 then. So one of these ones going around the inside of a cone. Quite a few things to do on this. Firstly, we'll call this angle theta. The reason this angle is quite nice to call theta is because if this is 0.6, think of that as 6 in your head, and this is 8, or 0.8, think of it as 8. Well, the 6/8 triangle has a hypotenuse, I believe, of 10. You should recognize it as just a scaled up version of the 3, 4, 5 triangle. So actually 0.6 squared plus 0.8 squared is 1 squared. And so this distance here is just 1. Now that isn't actually that necessary, but what it is good for is that we can work out sine, cos, and tan of theta super easily, because it's just 0.6 over 0.8, which is just 6 over 8, which is 3/4. So that would be tan. And the others will just be the other versions of the 3, 4, 5 thing. So that's going to be just written down there. We're actually not going to need the tan one, but the cos and the sine are super helpful, because now we can start labeling some forces. We've got mg coming down, obviously. We've got r perpendicular to the side of this cone here, coming up like this. And then our last force, I mean, maybe I'll resolve those first, actually. Yeah, I'll resolve those first. So we've got r, I mean, if this is theta, this is 90 minus theta. This is perpendicular to this, so therefore this is 90 minus 90 minus theta, and it's just theta again. So this angle is theta, which means this is r cos theta, and this is r sine theta. So theta to 90 minus theta, back to theta again, and the little triangle happens here. We've got one more force here, which is a frictional force coming down. Now, the reason the frictional force is coming down is because we're thinking about the greatest possible value of the angular speed. Now, if the angular speed is really, really big, what that's going to mean is that the particle, or whatever this is on the point of going up the cone, right? Like if it's going really, really fast, it's going to want to move itself up the cone, and friction will be holding it in place, going just around horizontally. So friction is acting downwards here, even though that feels counterintuitive, but it's just because the angular speed is very high. So okay, friction acting downwards, of course, it's mu r, right? As it always is. Mu being a quarter, so that's a quarter r. And we can also resolve that, right? Because if this is theta by alternate angles, this is also theta. So coming down, we've got cos, because that's next to the angle theta, and going across, we've got sine. So we've got all our picture filled in. The only things we could fill in now is, of course, that we know cos and sine are 4/5 and 3/5. We could put those in, but I'm not going to. I'm just going to write it out. Firstly, resolving vertically, we've just got that r sine theta, which is the one pulling upwards, is equal to mg plus a quarter r cos theta. We can put in sine theta and cos theta here, because sine theta is 3/5 and cos theta is 4/5. And we can actually get r in terms of mg, which is that, so that's useful. And the other thing that we'll do is we will resolve horizontally, but of course there's an acceleration horizontally, so we'll use F equals ma. Essentially this was using F equals ma, right? It's just that a is 0 upwards, it's because it's traveling around its own circle, not moving up and down. So this is just F equals ma or F equals 0, and then you just balance the forces. But for the horizontal, we have got F equals ma, because the acceleration inwards towards the center of the circle is given by this. I've got it written down, omega squared r. That's if you've got the angular speed. Before we used the actual speed, that was on the other one, the other question. But this time, this is the formula that we need. So we've got F equals ma. We've got a force, this coming into the center, and then of course the forces, and of course we've also got this force going to the center. So just those two things added together make m. So that's m, and then times a. R is just 0.5 because it's the circle it's traveling along has radius 0.5. And yeah, r is 5/2 mg, cos theta and sine theta are known values. You put them all in, and you end up eventually figuring out that omega at its greatest is this, because at its greatest, the frictional force is acting at its largest possible value, which is what we assumed in here when I put this value in here. So therefore, this is all going to come out to give me the greatest value of omega without the thing slipping up or down. Good. Question 7 then is the very last center of mass question that we're going to need to do. It is quite a long one. And the first bit of it is, I think, particularly difficult because you need to combine a lot of pieces of information that you're given about center of mass, but never really given all together in the textbook. Firstly, you're given this formula. We're going to ignore the cone for now. We're just working out the distance that this dome, once you rotate it around the axis, this dome makes, the center of mass, away from the origin. So it's an x distance here, so x bar. And of course, in a two-dimensional world, x bar is given by this. It's very similar to the y bar that we looked at, I think, way back in question 3 or 4 or something, I'm not sure. So, okay. But like I said, this is not a 2D figure. We're rotating this around to make a dome. So, but that's okay. We can shove in, in fact, actually, the first fix we need to make is that this isn't uniform. And this is a non-uniform shape. But that's okay, because we can just throw in this function into these two figures. So rho is just the function lambda over x squared. You're just allowed to do that. So just make a note of that. If you're doing it for non-uniform things, just throw in the function that's describing the density or the mass per unit volume into the two integrals. That's fine. But then, of course, you're doing a three-dimensional dome, not just a two-dimensional thing like this. But that's fine as well, as long as you just replace these with y squareds and put a pi on the end, because, of course, you're now doing a volume of revolution. And this is what I'm going to aim to do now, to find x bar, the distance away from the origin. So you just have to make those fixes, and then, of course, the algebra is just eventually going to come out. I'm going to deal with the bottom bit first. There should be a pi here. Apologies, I've just missed a pi from that. This, of course, is just the mass of the entire thing. So I've just called it m, and I'm just dealing with the bottom section first, because I don't want to put all of this integral on the screen at once. It's just going to make it just way too big. So we're just dealing with the denominator first for now. So just integrating y squared, which is, of course, 4a squared minus x squared. And then, of course, rho is just the density function, which is this, as I was saying before, integrated between a and 2a, of course. There should be a pi here, and there's a pi there. I just missed it on this one somehow. Anyway, pull the lambda out and multiply the x squared in here, or the 1 over x squared in here, I should say. Do some integrating, put in a and 2a, and it eventually falls out to be this, which is eventually this. And that's going to be the denominator. And what I'm going to do, again, just to make this a little bit easier for myself, is I'm going to say, okay, well, I've just figured out this is pi lambda a. I'm just going to multiply that over here, and then I don't have to write a fraction anymore, which just makes it easier. And now I'm just going to write this entire integral here as pi integral between a and 2a of course, y squared is here, the rho function is still there, and then we also tag on the x at the end here. And now I'm just going to focus on doing this integral. Firstly, expand this out, it just ends up having one more x than these ones did. Do a very similar integral. Of course, this time you end up, firstly, you can cancel the pi and the lambda, which is nice. But this integral ends up having a log, which is good because I'll see a log down here. And now put in the a and the 2a and cancel some things down. And eventually you find, of course, because log of 2a minus log of a is you divide them and you get the a's cancel, you get log of 2. Eventually, when you cancel the other a's, you get down to here. And I spent a long time staring at this, figuring out where my mistake was, why that wasn't a 5. But of course, it's just because this says center of mass from the center of its plane face. So essentially, I've just found the distance that the center of mass is from the origin. So I need to now take away this a to find this little distance here. So just do this, take away a, and you will end up with what they were asking for, which is good. Okay, now I've got a cone here, and now I know things about cones. Specifically, I know the formula for a cone. The distance of the center of mass is just in the formula book. So this is just from the formula book. It's a quarter h. So the horizontal distance from the center of mass of this cone is just a quarter of this, which is a across from its base. So this little distance here is just a. It's just a quarter of the height of the cone, which was 4a. So this distance is a. Now it says find the d, and d is the kind of combined center of mass of the entire toy. So of course I've got a center of mass this far, and now this little distance here is this number into the dome. And of course I need to sort of need to balance these out and get my overall center of mass somewhere in the middle of them. Now to do that, I can use the same kind of thing I was doing way back in question 1, which is the sort of overall center of mass across times the total mass of the entire toy is equal to this distance across times the mass of the cone, and then minus, because of course this distance, this center of mass, I'm just saying, is going the wrong way. So I'm kind of just assuming that the whole center of mass is towards this direction. It doesn't end up mattering. That's what these bars are for. You don't actually need to get these bars in your answer. It's just saying you can either have k plus 5 minus 8 log 2 or 8 log 2 minus 5 minus k. Either is acceptable, and it will just depend whether you put the minus here or the minus here. Like otherwise, it just ends up being the same. Now, the good news is we can be a bit lazy here because we're not told the masses, but we are told the weights, which is basically the same thing. So we can say the total weight is, or the total mass is kW plus 2W, and then we can just say this is kW and this is 2W, and then this thing here just falls out very quickly, just doing some very basic algebra, cancelling the W's, and you end up with it quite quickly. So that's all good to go. And then finally, we're going to suspend the toy from a point on the circumference of the dome, and it's going to, of course, hang so that this line here down to the overall center of mass is vertical. So now again, I'm assuming the center of mass of the overall toy is somewhere in the cone. It doesn't matter. You could do it the other way and it'd be fine. But this distance we just said is this, and of course this angle is alpha because it tells you, and it also tells you tan alpha is this. But of course, if this distance here is root 3a, then we can say tan alpha is just the distance we just found over root 3a. But they've told us tan alpha is 1 over 2 root 3. So now we can just solve this for k. We can cancel the root 3's and cancel these 2a's, and we end up with this. And now cross multiply and solve, and you end up with k as this. And even if you did it the other way around, and this was all masses, I think I tested this a while ago, and you just end up with the same number, so that's, or the same answer. So that's absolutely fine. You'll get it right either way, or at least hopefully you do. Anyway, question number 8 then is the simple harmonic motion question. Finally, we get to it. And yeah, firstly, we have tension, we'll call it tension 1 in this string, and we'll call it tension 2 in this string. Of course, we have the tension by Hooke's law is given by lambda x over L, where x is the extension and L is the natural length, which is 2 for both. So of course, we can say maybe something like, because this is in equilibrium, T1 equals T2. So we can say T1 is, or has lambda 20, L is 2, and then the extension we'll just call x. In this string here, lambda is 40, extension is still 2, and then natural length is still 2, but we'll call the extension y. And so now we can form an equation in terms of x and y, so that's good. What other equations can we form in terms of x and y? Well, because both strings have natural length 2, that means they're bridging a gap of another 2. So the extensions added together must be that missing 2. 2 plus 2 plus 2 is 6. So x plus y, the two extensions added together must be 2. Of course, we can solve this very easily. We get x is this and y is this. Okay, the extension in the left string is 4/3, and the extension in the right string is 2/3. Now, this natural length is 2. It's being stretched by 2/3, so 2 plus 2/3 gives us 8/3, I believe, which is what they wanted us to get, that one there. Now, part B, simple harmonic motion is given by this. Now, we need to set up T2 minus T1 equals mx double dot. X double dot is, of course, just A. Now, because these are the only forces in the picture, right? So F equals ma. Now, let's just imagine that this has been pulled across. I can kind of ignore this whole midpoint thing for now. I don't really care about it for now. Let's just imagine this has been moved some distance to the left. So therefore, the left string is stretched. It is less stretched than it was initially. And the right string is more stretched by some, let's just say by some distance x. Okay, what this is saying here is that the new tension in the right-hand string is still lambda x over L, but x is now the 2/3 it's originally centered, plus some little distance x that it's newly extended by, if I'm just imagining this is just slightly to the left of where the equilibrium point is. And likewise, this one over here is the same tension as it was before, but x is now 4/3 minus that little extension that's been moved away towards the left like that. So this makes this. Now, where's this minus come from? Well, because if I'm taking x to be a positive value towards the left, which is what I'm doing here, the acceleration, of course, acceleration always acts towards the center of the simple harmonic motion. The center, of course, is going to be at the equilibrium point. If I'm over here somewhere, the acceleration is towards the other way. It's towards the other way that I've said x is. So x is positive this way, which means acceleration is going to the right towards the center, which means the acceleration is negative. So that's where this negative comes from here. And now, of course, we can just multiply this out. These numbers cancel, which is great. And you end up with this. You divide by that, and you end up with this. Now, if you forgot about any of these minuses, of course, you can just fiddle with this until you end up with something that looks exactly like this, which is exactly what you should do. So, for example, if you forget the minus here, and you end up with x double dot equals 100x, just throw in a minus and pretend like you know what you're doing. And you'll end up with a minus down here, and you'll get 4 marks anyway. So that's exactly what we should do. Anyway, the time between the instant P is released and it returns to point E is s seconds. Now, let's go back to this. It's released from the midpoint of AB. So that's the furthest to the left it will ever be. It will initially go towards here, then down here, then back here, and then back here again, and that'll be a whole period. And of course, if it goes from here to here, that's the middle point, to here, to here, to here. Well, then just here to here is just a quarter of that whole thing, right? 1, 2, 3, 4. So what we're looking for is a quarter of a period. But we know the formula for a period if we know omega, which is 10. So we're just going to find the time it takes to do a period. You need to know this going to the exam. And then just divide that by 4, and we'll end up with a time for s. Now, finally, to end this exam, it says find the length of time for which the speed is more than 2. Now, I decided to use this formula just because I really like using this formula. V is 2. So let's just find the places on the motion where the speed is 2 first. Omega is 10. Of course, A. Now, A is not immediately obvious, but of course, if EB is 8/3 and it's being released from the midpoint, well, the midpoint is 3 away from B, which is 9/3. So it's just 1/3 from E to the midpoint. So the amplitude is just 1/3. And now I can use all those values to find out the 2x values for which I'm traveling at speed 2. So essentially, either 4/15 this way will give me a speed of 2, or 4/15 that way. And of course, speed is most in the middle of simple harmonic motion. So I want to be between those two figures there. Now, the only way I thought to go from speed or get to speed from here was, or sorry, to get to time from here was using this formula. This is the formula for if you're starting at the end point of the simple harmonic motion. Again, this I don't think is in the formula book at all, so you just need to have that memorized. It's different if it's traveling from the middle, of course, but this is if it's doing the end point. And now what I can say here is I just want to find the time for which I'm traveling at 4/15 and likewise minus 4/15. I'm doing this in radians, of course. I'm sure you can all solve this equation. You get this. If you do minus 4/15, you get this. So essentially, it takes 0.06 seconds to get from the endpoint to here, where it's traveling at 2 for the first time, and then this long to get to traveling at 2 the second time. And I want all the time in between that. So essentially, I'm just going to do this figure minus this figure, except it says one whole oscillation. One whole oscillation is from here all the way to there and all the way back again. So I actually want two lots of those intervals for my total time, which is just this figure here, and that'll be the answer. Thanks for watching, and I'll see you next time.